In today's lesson, we are going to be introduced to what it is a finite state machine and how they are used in programming and specifically in game programming. Okay. First of all, in case that you don't have the code of the project we did the last lesson, you can download it from here and we will start from there. Okay, so what's a state? What's a finite state machine? A finite state machine is a series of different states that our game elements can be. In each state, it's run a series of code instructions that it's relative to the behavior associated to that state. These diagrams are something that usual for game designers. So we are going to translate these designs to code. Okay. In this image, you can see a very simple finite state diagram of the behavior of a dog. The dog in the idle state can be either hungry or maybe it can detect a danger. If it's hungry, he will go to the kitchen, and if there is food in the kitchen, he will eat the food. If there is no food in the kitchen, then he will bark. Okay, and if he has eaten the food, then he goes back and is satisfied. He goes back to the idle state. In the other path, if he has detected a danger, he will start barking, and from this state, if he is too close to the danger, he can bite the danger, or after biting the danger, maybe he can go back to the state of barking. If it's a false alarm, he will go back to the state of idle. So this is a very basic representation of what would be the behavior of a dog represented in a finite state machine. Okay, so what we are going to do in this case, we are going to create this finite state machine for the class player, and we are going to do it together. Okay, so we are going to identify the states that can be the player. In order to work, there is this tool that I am using for anything related to diagrams that is pretty useful. Okay, so let's put the two screens together. Okay, and now we can start thinking about creating this finite state machine that will represent the behavior of our player. We are going to try to keep it as simple as possible. So just think about it. What first state we would create. If you have thought about the idle state, you would be right. In this idle state, the player will stay put, will stay in this exactly the same place. Okay, we are going to create another state. In this other state, just think for a second what other state we could have aside from idle. What can happen in the idle state that can make change from the idle state to another state? What can possible happen here? To keep it really simple, I have thought about the state of walking, the state walk. Okay, and to create a transition between the two states, we have these arrows, okay, that we can use to connect the states. Okay, and we can add a text that tells us the reason why there is a transition between the idle state to the walking state. In this case, just think for a second what should happen in order for the player change from the idle state, where states put does nothing, to the walking state, what should happen. Okay, if the response is to press the arrow keys, you would be right. So when the arrow keys are true, the transition should happen. Okay, let's give it a little bit more space. Okay, from the walking state, what could you think about a way to transition from the walking state to the idle state? What should happen? Okay, let's create the connection. One to here, one to here. Okay, so if you have thought that the only thing that should happen is that the user has stopped of pressing the arrow keys, you would be right. Okay, so when this is false, when he is in the walking state and stops pressing the arrow keys, he should go back to the idle state. Okay, so here we have our most basic finite state diagram to represent the player. We are going to add a new another state. Okay, what other state is really typical when you are developing a game? Okay, in this case, the state that I have identified is one of the things that are most common in almost all video games, is that our player can die. Okay, so let's make the connections. So we have that in the state idle he can die, and also while walking he can also die. Okay, so let's make the connections and let's find out what makes the transitions between idle to die and walking to die. What do you think that makes the transitions between these two? If you have thought about when the life is 0, you would be right. Okay, so the condition that the system must meet in order for the player to go from idle state to die state, it should be that the player's life should be 0, and exactly the same should happen for the transition between the player in the state walk to go to the state die. Okay, so that's our first designed finite state machine diagram that represents the behavior of the player. Okay, let's summarize what we have done. We have started creating the idle state, then the walking state, and the transition between the idle state and the walking state, it will happen when the user is pressing the arrow keys. When the user stops pressing the arrow keys, if it's in the walking state, it will go back to the idle state. And if either in the idle state or the walking state the life is 0, it will transition to the state die. Okay, so that's our first. Now let's do the next step in the sequence to convert this to code. The next step would be to translate our diagram design to a table design. To make this table design will help you out in order to identify any connections that we may have missed in the finite state diagram. Okay, so what can we see here? It's just a table, so we will have rows and we will have columns. Okay, and both on the rows and the columns we are going to put all the states that we have identified in this previous stage. Okay, so right here, for example, in this particular case, we would have well, let's do it. In this particular case, for our 3 states, we would have 3 rows. Okay, idle walk die, and 3 columns idle walk die. Okay, so what represents this this table design is to have a more clear picture of the interactions between the different states. Okay, so in the table what would be represented is that when an state like idle and another state like walk join in the column and row, we should put the condition that should happen, for example, for the idle state to transition to the walking state. Okay, so we would be translating this graphic representation to a table representation. Okay, so we have the idle state, and if this condition happens, if the user is pressing the arrow keys, it will transition to the walking state. Okay, the same would happen if we are on the idle state and we check that the condition that the life is 0, then we will transition to the idle state. That is the same that we are representing here. If we are on the idle state and we detect the condition that the arrow keys have been pressed, we transition to walk, and if we detect the condition that the life is 0, we transition to die. Okay, so we are making this representation through the table. Idle detects the arrow keys, go to walk. Idle detects life is 0, go to die. The same would happen for the rest of the cases. If we are on the state walk and we are detecting that the user has stopped pressing the arrow keys, we will go back to the idle state, and like it is being shown here, if we are on the state walk and the user has stopped pressing the arrow keys, it will go back to the idle state. So that's what's happening here. Walk, detected that this condition has happened, go back to the idle state. If we are on when we match the same states, okay, here we can put the actions that are performed in these states. For example, in the case of walk, the action that is performed in the walk state would be to move. Okay, in the case of idle, there is no action, because for the moment we understand that we are not going to do anything there. There is no action here, but in the walking state there is action. So when the row is the same as the column, here we would put the actions that the game is going to perform for this specific state. In this specific state, we are going to move. Okay, next, from walk to die, okay, the same as from idle to die. The life must be 0. Finally, from the die state, you may have noticed that there is no transition back, neither to idle, neither to walk. So this die state, nothing would happen in either of there would be no transition to idle, no transition to walk, and the actions that can be performed on die, for the moment no actions are going to be performed on die. Okay, so this would be the translation from the finite state machine diagram to the table design diagram. Okay, this step will help us out in order to go to the next step, that is to translate this table to what we know as pseudocode. Pseudocode is just a way to express how the code is supposed to work, but without using any specific programming languages. You can use your own natural languages to do it. You don't have to worry at this stage of the process of worrying about everything that means programming. The goal of this is to do another step in the process to translate from this diagram to the final code. So this is another step in the process that will help you out in order to to make this translation. Pseudocode is something personal. Depending on each person, they will create one pseudocode or another, because this is not a programming language. This is just an intermediate step to produce languages. So here you can see just an example of what could be considered as pseudocode for this particular case. Okay, so to translate this table to the pseudocode, we start first evaluating the state where we are. We are just checking, okay, in what state we are. Okay, the first thing we will do is just to create the three states. So we would start just okay. We are checking the state. What states do we have? We have the state idle, the state walk, and the state died. Okay, so let's create the pseudocode. Okay, we are going to do the actions of the state idle just right here. We are going to do the actions of the state walk just right here, and we are going to do the actions of the state died just right here. Okay, this would be the first step to create the pseudocode. We have expressed in our own natural languages what's going to happen. So let's start, for example, for the case of the idle state. Okay, so the first action we would do, let's check the table. Okay, we are on the idle state, and we have to check that if the arrow key press is true. Okay, then if that happens, then we can transition to walk. Okay, so how we can express it in our own natural language? So we are translating that. So if the arrow keys are pressed, okay, see this, if this is true, then we should in this particular case change the state. The state should change to the state walk. Okay, so we would have implemented in pseudocode the first transition, the one that transitions between idle and walk. Okay, so if the arrow key is pressed, go to walk. Okay, so we are getting that. So if the arrow key is pressed, then we should change the state to walk. This is expressed in our own natural languages. Okay, next, what do we have here? Okay, we are still on idle, and we have to check if the life is 0 to change the state to die. Okay, let's do it. Let's type the pseudocode. So if the life is 0, then we should change the state to die. Okay, another condition that we have expressed in pseudocode that represents this transition right here from idle to die. Okay, so we are going to the next state, to the state walk. Okay, right here, and let's check the table, and the table tells us that okay, there is a transition to idle when the arrow keys pressed are false. Okay, so let's express it in our own natural languages. So we have, if the arrow keys pressed are false, then we should change the state back to idle. Okay, okay, good. Okay, more. Okay, also if we are on the state walk, okay, walk and walk, we should move. Okay, so let's do it. Okay, we should move. Okay, in this state we should run the action to move. Okay, so we got it right there. What else? Okay, the final condition of walk would be if checking the life again. If it's 0, to go to die. Okay, so let's do it. We can even copy paste because it's the same. We are checking the life to 0, then we should die. In the case of dying, well, there is no action, no transition, but we can still put something right here. Okay, so what we can do is just to put some log message. Just print a log message. The player has died. Okay, so we have translated our table to pseudocode. Okay, we started by just evaluating the state. Next, we created each of the states like this. And then we went through the table just checking, okay, what's the transition from middle to walk? Arrow. Okay, so the transition is this one. Then the transition to life. Then we continued with the state walk, and we did the same. Okay, move belongs when it says in the state walk, and the other transitions to the other states, and finally the state die. Okay, that is the translation from the table to the pseudocode. You have to understand that there is no wrong answer creating the pseudocode, as long as it makes sense. We can say we are changing the state to die. You can express any way you want, as long as you are able to understand it. You can express yourself any way you want. There is no wrong answer as long as you are able to understand that. Okay, but the more similar to the code you do it, the easier it would get. Okay, so the next and final step in this process is just to translate the previous pseudocode to real code. Okay, so we are going to go to the Unity project. Okay. And here we are going to create first all the necessary elements to have this finite state machine. We would start with just the declaration of the variable mState that will keep the current state. Okay, so we are going to declare it in the avatar class, because all the elements that inherit from avatar are going to take advantage of this variable. Okay, next on the player state class we would create these constants that each constant represents each of the states we have identified. Okay, we have the state idle, the state walk, and the state die. And the next thing that we are going to do is just in the update of the player script, we are going to create just the structure, just the skeleton of our finite state machine. Okay, so we are going in the update, we are going to declare just the skeleton, the structure that would be our finite state machine. For the moment we can comment this, do not remove it. Okay, now let's start by implementing the first method that we are going to use. That would be the arrow key pressed, that will identify if the user has pressed any of the arrow keys or not. So go ahead and implement this function that will return true if the user is pressing the arrow keys, or false if the user is not pressing the arrow keys. Okay, so go ahead. Okay, and the implementation of this method should look similar to this. We are checking if any of the arrow keys are being pressed. Okay, by using the utility input get key down and each one of the keys of the arrow keys, and also we are checking the keys A, W, S, D, because they are also used as the arrow keys. If any of these keys is pressed, then it will return true, and if none of these keys are pressed, then it will return false. Okay, so now we are going to use this function in our structure. So in the method update, you have to implement translate the pseudocode from pseudocode to real code, and we are going to focus our work in these two first conditions. In the case of the state idle, we are checking if it's true, the arrow key press to change the state to walk, and in the case of the state walk, we are checking if the state is false. And if the state is false, we are going back to the state idle. So go ahead and implement the code. And the code should look something similar to this. We are just using the conditional if just to check if our method that checks the arrow keys returns true or false. If it returns true, we will change the state from idle to walk, and in the state to walk, if the arrow keys are not pressed, we change the state from walk to idle. Okay, let's test if this implementation works. In order to do that, we need to include a couple of debug log messages. First one in the state idle. Okay, so in the state idle we put a debug log message that will be displayed for every frame that happens in the state idle. And we will do the same for the state walk. For the state walk, we will use another debug log message that will tell us that the player is in the state walk. Once we have these two debug log messages, we can go to the code, and if we press the arrow keys, we should be able to go back and forth between the state idle and the state walk. First of all, use collapse. Okay, so you only have one debug log message, and just right now we are going to press any of the arrow keys. In 3, 2, 1, the arrow key is pressed. I keep pressing the arrow key, and I am going to release it in 3, 2, 1. We are back to the state idle. Okay, so another time, press any other of the arrow keys. I am going to the state walk and releasing the arrow key. I am going back to the state idle. Okay, so this is working. Let's move forward. Okay, so the next step would be keep implementing the pseudocode, and we are going to check the player's life now. In order to check the condition of if the player's life is equal to 0, then we change the state to the state die. Okay, so go ahead and implement this condition in real code. Okay, so the code should look like this. We are checking the life, if the life is 0 in this if conditional. If the life is 0, we are changing the state from idle to die. okay, and we are doing exactly the same in the case of work, checking if life is 0, and if life is 0, the player should change the state to the state die. Okay, so what we are going to do next is this code right here. You are going to use it in the different parts of our skeleton, of our finite state machine. Okay, so think about where goes where. You have a pretty good idea if you check that pseudocode, at least where is going something, but check where is going the other things. Okay, so go ahead and do it. Okay, and the code should look similar to this. So what we have done is that in the idle state we are going to perform some operations. The only operations that we are going to perform in the idle state is that we allow the user to rotate the player's camera, and we allow the user to be able to shoot. And in the state walk, aside from rotating the camera and shooting, we are also going to move. If you remember, we had in the pseudocode that for the state walk we had the action of moving. Okay, and if you recall, in the table we had here the action of moving. Okay, so we are doing just that. For the state walk we are moving, and we are doing some more actions there. Okay, so it's time for us to test it. Okay, so let's go back to the code. Let's press play. Wait, just 1 second, because we need to see somehow that we are on the state die. So in order to just to know that we are on the state die, we are going to just show another debug log message here telling us that the player is dead. Okay, with that log message would be enough to know that the player's life has been detected as to be 0, and the transition has been performed, and we are on the state die. So we can now go to the Unity editor. We can just press play. Okay, and well, it seems that first of all, just to know that we are on the state idle. Okay, messages keep appearing on the state idle, and if we press any of the arrow keys, we are transitioning to the state walk. Okay, so this is right. Okay, cool. Okay, so the next state that we need to check is the state die. In order for the player to die, we are going just to collide with the spikes until we get our life to 0. Okay, 70, 50, 20, and again in the 20. Okay, 0. So if you can see here, we are on the state dead, and we keep printing in the debug console the message that we have defined for the state die. Okay, so our finite state machine seems to be working fine. And a small change that we are going to do in order to ensure that, well, in case that the player's life goes below 0, we are still interested to go to the die state. Okay, because right now we are only checking that the life should be 0, but maybe the life it could go below 0. So we are just going to put this conditional that tells us that if the life is below or equal 0, we are going to the state die. Okay, so just do that, and let's test it again, and collide freely with the spikes. Okay, so we are going crazy with the spikes until, okay, the player is dead. And the other thing that you should notice is that we have not interaction right now. We cannot move, we cannot shoot, we cannot do anything. That's why we are on the state die, and on the state die there are no actions performed here. The only action that is performed is just the debug log message that it's being displayed right here. Okay, but aside from that, there are no actions, no move, no rotation, no shoot, so we cannot do absolutely nothing here. So okay, so our finite state machine is working fine. Okay, before moving forward with the lesson, we are going to do a small change, but it will have a really big impact in the sense that it will help us a lot, this small change. What we are going to do, instead of we were just assigning to mState to our variable, we were assigning like our state die, our state walk directly. Okay, so what we are going to do is we are going to create a method, change state, okay, in the class avatar, and we are going to use the extended the override in order to perform some operations in the exact moment we are transitioning of a state. Okay, we are interested that in the exact and only moment that you are changing the state, we are interested to be able to perform some one-time operations. That's the reason why we are going to do this change. Okay, so let's go back to the code, and in the avatar class we are going just to implement this method. Okay, so you can copy paste. It's protected. It will inherit. It will be inherited by all enemy, bullet, NPC, and player. Okay, and the only thing that it does, it just receives as a parameter the new state that the mState variable should be assigned to. Okay, and in the player class we are going to override it to extend it. Okay, so you can also copy and paste this code. Okay, just right here. And what we are doing here is, okay, we are overriding the behavior that we are inheriting from avatar. We are calling the base class. If we press F12 to go to the definition, we are going back to the avatar to this assignment of the parameter to the variable mState. Okay, and after that assignment, okay, so what we are going to do just for the moment, just to display a log message that it will be only printed once. Okay, because we are interested to know exactly just the moment that the state has been changed. In that particular instance, in that unique moment, we would be able to later in the future implement some functionalities just to our program do whatever we want to do. Okay, so after having implemented both in the avatar and the override in the player, what you should do is just use it. Okay, so go ahead and do the necessary changes in order for this to work. Okay, and the code should look like this. Okay, so before we just had that we were assigning the value of the state directly. Okay, just like this. And right now we have changed that by this method. Okay, so the flow would be that, okay, we are interested to change the state from idle to work, so this method would be performed. So we go to this method goes to the base. In the base we are just updating the state with the new value, and after that we are checking, okay, what's the new state. In that particular moment we are going to perform one-time operations, the operations that are only performed just in the moment that it changed the state. So these three debug log messages are going to only be printed once. Okay, for we are going for the moment to comment this other message, so we can just test that this is working. Okay, so let's comment all these three messages and let's test it. Go back to the Unity project, press play. Okay, so the first change state, that is state changed to idle, has been performed correctly. It's just one message. Okay, let me hide one screen. It's only one message. Okay, and if we press the arrow keys, we are going to transition to the state walking. In 3, 2, 1, we have transitioned to the state walking. Okay, and it's only one message, and when we release the key, we are going back to the state idle. Okay, so we are getting just this one time actions. The final check that we could do is just to test the die state, and the die state is triggered, and once we are here there is nothing we can do but to stop the application. Okay, as I said, this would allow us to perform operations in the exact moment that we are changing the state. This would prove extremely useful. So in the next step, what we are going to do, we are going to create the finite state machine, this time for the enemy. In this part, you are going to take the lead, in the sense of you would be responsible to create the finite state machine diagram, then the table, then the pseudocode, and finally the real code. Okay, so what you are going to do is that we are going to create a very basic enemy. We are going to create a sentinel enemy. Okay, and you should define the states and transitions to describe the behavior of this sentinel enemy. And the sentinel enemy will perform like this. The sentinel will stay in its initial position, checking for if the player enters inside its detection radius. Okay, once the player has been detected, the enemy will walk towards the player. If the enemy is at shooting distance, then he will stop and will start shooting to the player. Okay, and if the player leaves the detection radius of the enemy, the enemy will return to the initial position. Okay, so this is the behavior. You first should describe it with a finite state machine diagram, then a table, and then a pseudocode, and finally with the code. For the moment, let's go one step at a time. Okay, and let's do the finite state diagram. Okay, so first of all, go to the diagram editor, and here we are going to create our finite state diagram. Okay, so the final state machine diagram that represents our sentinel enemy should look similar to this, but it shouldn't look exactly the same. Is it possible that you have created more states or maybe less states? Well, that's not very possible, less states than this one, but this is not just a unique solution. There are multiple available solutions. So if your finite state machine diagram is different from mine, it's not a problem as long as it represents somehow the behavior that we are looking for. Okay, so said that, let's describe what I have done here. Okay, so the sentinel should be checking initially for the player. If the player is in range, then he will walk towards the player, and if the enemy is in shooting range, then he will start shooting to the player, and if it's outside the shooting range, he will go back to follow the player, to go towards the player, and if it's totally outside the range of the enemy, then the enemy would go back to the initial position. In the three states, the enemy life can go to 0 if the player has shoot to the player to the point that the enemy is dead. Then in any of these states, the enemy can be killed. So we have to check the condition that if the life is 0, then the enemy will go to the die state. Okay, so we are checking in all the states if the life is 0. So the next step would be to create the table that represents the finite state machine. Okay, you can download this template that contains all the lines to ease the process. So you can just click on the link and you can download the file, and if you go to the diagram editor and open the file, you should get this table right here. So the steps that we have explained that we should do is just to place all the states in both in the rows right here and both in the columns right here. Okay, and you have to make the translation from the finite state machine diagram to the table diagram. So go ahead. Okay, so the final result of our table should look similar to this. Okay, we have just placed first the states both in the rows and in the columns, and when we are checking what conditions should be met in order to change from one state to another, we go back to our finite state machine diagram and check what's required to make the transition. The actions for the check for player state, it would be just to go to the initial position, okay, and if for the check player to transition to go player, it would be that if the enemy is detecting the player inside the detection range. From the check player to the shoot player, even though there is no connection between these two, but as I have said, the table allows us to detect relationships that we were not detecting before. So if this happens, that we are on the check for player state, and directly we are getting inside the shooting range, then we should transition directly to the state of shoot to player. And finally, all the three states transition to die when the life is 0. Okay, so there is the transition to die when the life is 0. Okay, for the go player state, to go to the check player state, let's check the diagram. Okay, from here to here, it's when the player is outside the range. Okay, so if detection range is false, if it's not in the detection range, then go back to the state check for player. Okay, in the state, the actions that would be performed in the state go to player would be that to walk towards the player. And from go to player to shoot to player, the condition that must be met is player in shooting range. Okay, so yes, if it's in shooting range, then transition to player, and the final transition to die state when the life is 0. Okay, next in the state shoot to player, let's identify the transitions. From shoot to player to check to player, we cannot see any transition here, but the table helps us to identify some missing transitions, and we can proceed to say, okay, so yes, there will be a transition from shoot to player to check for player if it's directly outside the detection range, when this condition is false. Okay, from shoot to player to go to player, there is in the finite state machine diagram, there is a transition there, so we are putting that if it's not in shooting range, then go back to player, and the action that it's going to perform on shoot to player would be just that, shoot to player. Finally, the transition to die. And finally, for the state die, well, there is no transition to go back to any of these states, and as an action to be performed in the state die, we can say that it plays a die animation. Okay, so the next step in our sequence to create the code for a finite state machine is to create the pseudocode. Okay, as I said, the pseudocode is not a real language. It's something that it's personal for everyone, and it's a way for you to describe in your own natural languages the description of this table. Okay, so go ahead and describe this table in your own personal pseudocode. Okay, Okay, so the final result should look something similar to this. So what we have done is just to create the pseudocode based on the table we made. Okay, we started with the check for player state. The action that must be performed in the check for player state is go to the initial position. Okay, so we are running it first. Next, we are running all the possible conditions to transition to different states. Okay, we are starting with is in detection range. Okay, this one, and if this happens, then we transition to go to player. Okay, next condition, if it's in shooting range, okay, then shoot to player, then transition to state shoot to player, and finally if we detect that m life is 0, then transition to the state die. Okay, and we are doing exactly the same for the other states. For go player, the action is walk to player, and the conditions to transition to the different states are when it's outside the detection range, go back to check player. If it's inside the shooting range, go to the state shoot to player, and if the life is 0, then transition to the state die. Next one, shoot to player. The action that must be performed in the state shoot to player is just that, shoot to the player. And the conditions to transition to different states are, okay, that is in detection range false, then go back to check to player. Okay, if this is false, then go back to check to player. This one is okay when it's in shooting range false, also go to player state, and finally check if the life is 0 to transition to the die state. And finally, I have changed the action on die to an action of destroy the same enemy, just to make it disappear. Okay, for the moment we don't have animation, so just we are going just to destroy it, just to get a visual feedback of that the enemy has been killed. Okay, so once we have our pseudocode, it's time to do the final step, do the code. So the first thing that we are going to do is that in the enemy script we are going to create the constants that will represent the different states. Okay, and in the same script enemy, on the update method, you are going to create just the skeleton, the switch evaluating the state, and with each of these cases in that switch. Okay, after that, what you are going to do is just to create the definitions of the functions that we have identified here. Okay, and for the moment you are just going to leave them empty. If it's a method that doesn't return anything, you don't need to put anything, but if it's a boolean or if it's a function that returns something, just return a value in order for the compiler not to complain. Okay, so go ahead and first of all declare the constants that represent the states. Next, create the switch with all the cases, and next declare all the empty methods. Okay, so go ahead. So the whole thing should look like this. You have first declared all the constants that represent the different states. Next, you have created just the skeleton of the skeleton of our finite state machine right here, and you have implemented or declared only the methods that we are going to use inside our finite state machine. Okay, so now that we have just a skeleton, okay, we are going to fill that skeleton with the results of our pseudocode. Okay, so what we are going to do now is just to finally finish the translation process of the pseudocode into the code. Okay, so let's go back to the code. Okay, and we are going to implement the pseudocode. That's why it's interesting that the pseudocode can be really similar to the final code, because this process would be easier to do. Okay. Okay, so just like this, we have filled our skeleton, okay, with the pseudocode that we had done in the previous step. And on the next step, what we are going to do is just to completely implement these methods that are right now empty. Shoot to player, is shooting range, is in detection range, wall to player. All these methods are just right now, they are empty. Okay, we have just focused our work just right now in filling the whole architecture, the whole skeleton of our finite state machine. And the next step would be just to implement these methods so we can get a working finite state machine design. Okay, but before that, the next step is just like we did with the player. We are going to extend the change state just to print a debug log message only in the exact precise moment that the state changes. Okay, so you can just copy paste in this case the whole thing and we can just explain it. Okay, so go back in the code, and here, well, we are just extending the method change state. Here in the declaration of change state, F12 to go to the definition, we are just assigning the state, and we are evaluating in which state the enemy has just changed to. Okay, and in this case we are just displaying a debug log message. Okay, the next step, we are going to implement some methods before dealing with the methods we have defined in the pseudocode, in the whole process. So the first method that we are going to code is the method getDirection. Okay, the method getDirection is going to get the vector that should be used to go from an origin point to a target point. Okay, this method will prove pretty useful in order to use it in multiple operations. And okay, we are going just to put this method on the avatar script. Okay, so let's go to the code, and on the avatar script we are going to place this method, so everybody who inherits from avatar can use it. Okay, so this method getDirection receives two parameters, the target and the origin. Okay, and what it calculates is the difference between the target and the origin, and this vector value would be normalized. That means that the magnitude of this vector it's 1. With normalized vectors you are able to use it freely for any kind of operations related to movement, so it's pretty important to normalize the vectors if you are going to later use them in movement operations. Okay, and yes, it will return this direction vector. Okay, this would be later used in enemy to get the direction from the enemy to the player. So next, another important thing to code before proceeding is that the enemy class can get a reference to the player. Okay, so on the enemy script, okay, we are going to declare a private variable member that would be the reference to the player. Okay, and we are going to initialize this private variable member in the start method. Okay, so in the start method we are going to look for the game object that has the component of type player. Okay, this one right here would be the type player. Okay, so we don't get any compilation error. Okay, good. We can just right now take advantage of this information. As you can see here, we are getting the player when this condition happens. So since we are already getting the player from here, we can replace the whole thing just right here. Okay, so now it's the time to finally implement the functions we previously declared in our code, that we left them just empty. So now it's the time to fill them. Okay, and we will start with the function is inside the detection range. Okay, so the method is inside detection range. What it's going to do is that it's going to detect if the player's position is close to the enemy position by a certain value. Okay, as the first step, you can get the player's position from the accessing through the player reference to the game object to the transform. You get the position. Okay, please use the vector3 distance to calculate a distance in between 2 points. Okay. And the third tip is that remember to declare a public member variable that it will be called the detection distance, and this value is the one that you are going to be able to adjust in the Unity inspector, just to adjust which detection distance you are going to use to detect that the player is considered to be close to the enemy. Okay, so please go ahead and implement the method is inside detection range. Okay, and the code should look like this. So in the function is detection range, what we are doing is first the conditional if, because we want to check if the player's close to the enemy, and we are using what I told you to use, the vector3 distance that calculates the distance between 2 points. And the first point that we are getting is the player's position. We are getting the player's position through the previous reference that we got right there, and we are getting the second parameter of the current position of this enemy. Okay, so calculating the distance from the enemy to the player, we get a value, and we compare this value with a public member variable that we will be able to adjust in the inspector. Okay, and if this value is below that distance, okay, we are returning true. We are returning that the player is inside the detection range. If it's not in this detection range, we will return false. The next method we are going to implement would be is inside shooting range. Okay, it's really similar to the previous is inside detection range, so you can take that as a template. And well, you would have to create another public variable member to be able to adjust the shooting distance. So go ahead and implement it. And the result should look like this. Okay, as we did before with the detection range, we are calculating the distance between the position of the player and the position of the enemy, and we are comparing that value with a new public variable member, distance shooting, that we have set to 5. This would be adjustable in the inspector, so we can customize our enemy the way we want. The next method that we are going to implement will be go to initial position, and this method will instruct the enemy to go to an initial position. Okay, so the first tip to implement this behavior is just to create a private member variable that will keep the information about the initial position. We can take just the same position where it starts the enemy as the initial position. Okay. The second tip is that if you remember, we created the function getDirection to get the vector that would allow us to move in a certain direction any kind of object. Okay, so use that function to get the direction to move forward to that position. Okay, The third tip would be just use the existing method that you can inherit from Avatar. You are inheriting right now from Avatar, that will allow you to move the enemy in the direction we want. And the fourth tip would be that when the enemy you have to detect when the enemy is close to the position, then it should stop moving. Okay, so you have to check if it's close to the position, and the moment it's close to the position, he should not move anymore. Okay, what you should have to do in this case is just to use the if conditional in order to check the distance with the initial position, and in case that the distance with the initial position is below a number that you decide, then the enemy should stop moving because it has reached the initial position. Okay, so go ahead and implement this behavior. And the result should be similar to this. What we have done is we have created a private member variable where we were going to store just the initial position. Okay, we initialized, set the value to that initial position just in the start method. We set the value to the current position of the enemy. And in the go to initial position method, what we are doing is we are doing it wrong. Okay, so if the distance between the initial position and the enemy is above 1, then the enemy should move in the direction to that initial position. Okay, the moment this distance is below 1, it will stop moving. Okay, so we can do what we can do right here, just debug log message, just telling us that we have the enemy has reached the initial position. Okay. The next method we are going to implement would be the method walk to player. Walk to player would be a little bit similar to the go to the initial position, in the sense that the first tip is that we are going to get the direction vector in order for the enemy to go towards the player. Okay. And the second tip is that we are going also to use the move to position method in order that with the previous direction vector move towards the player. Okay, so go ahead and implement the method. Okay, and the result should look like this. First of all, we get the direction vector in order for the enemy to go towards the player. Okay, and next we are just using our method move to position in order to use the previous direction vector with the speed and the adjustment of time delta time. Okay, if everything is in order, you should be able to run it in the Unity editor, and the behavior we are going to get is that when the player gets close to the enemy, gets inside its detection range, then the enemy will move towards the player. The enemy then will stop when the player is in shooting range, okay, and the enemy should return to the initial position when the player is outside of range. So let's do it. Let's test it. Let's restore the speed of the enemy. Okay, let's start with this one. We are going to restore the speed. For the moment, I think that we are good with a speed of 5, I think. And what we are going to do is for the objects, we are going to disable them, okay? Because right now we are not interested that the enemies can die, okay? So for the moment we are going to disable all related to the spikes and the portals, okay? So we are good to go. We can press play, and if we get close to that enemy, the enemy is getting closer right now because it has detected that it's inside its detection range, and in a few seconds it's going to now the enemy has stopped because it has reached the shooting distance and is right now shooting. Okay, it would be right now shooting if the shooting would have been implemented. Okay, we are going to move away from the enemy, just for the enemy to go back to the initial position. Okay, as you can see, slowly the enemy is going back to the initial position, and I think it's there. Let's do another test, changing the speed of the enemy to make it more visible. Let's make it 20. Okay, and try it again. Okay, so we are going to, we have a small problem, that is that the initial position is just a few meters above the ground. So the enemy is just trying to get to that initial position. So what we need to do is to adjust that the enemy starts as close as possible to the floor. Okay, so with this the enemy should stay in the same position. Okay, so we are good. So now if we get close to the enemy, okay, the enemy has moved forward the player and it's in shooting range. And now let's move away from the enemy, and the enemy is moving back to the initial position. Okay, again moving in detection distance. Now he has get close to the shooting distance and moving away. The player is going back to the initial position. Okay, this part of our finite state machine is done. The next part would be to implement the shooting behavior. The final step that we are going to implement would be the implementation of the method shoot@player. In this particular case, I will help you out to implement this method. But in case that you want to take the lead and do it by yourself, just go ahead and do it, and come back to review how we did it, just to check if the solutions are similar. What we are going to do first is in the code we are going to create a public member variable in enemy that would be the reference to the prefab of the bullet that is going to shoot the enemy. Back in the Unity editor, we are going to create the bullet enemy. Okay, so, and what we can do is just to take our the bullet we are using for our player, and we are going to assign it just another material. Okay, first of all, just unpack it, because we want to create a new one, rename it to bullet enemy, and to this new bullet we are going to assign it a new material. Okay, so we can just assign it a red material. Okay, and finally we are going to create the prefab just by dragging the whole thing to the prefabs folder. Okay, so here we have our bullet that inherits, that contains the component bullet. Okay, has a speed, has a damage, has a type. Okay, and we have created the prefab, so we can instantiate it in runtime. We can remove it from the scene. Okay, and let's do another thing. Let's rename it also the bullet that we are using for the player as bullet player, and we are going to assign it also a different color. For example, we have here green. We can use the green color. Okay. Okay, so we have these two prefabs. Just make sure that the player still makes reference to the bullet player. And now we can go to our enemies. Okay, we can try to group the enemies in another game object. Enemies, just place them all in the new object, and we can do the same for the NPCs. Okay, good. Okay, so for the enemies we can just select them all and just drag the new bullets to the new public variable member that we have previously created. Okay. Okay, so right now we have the reference to the bullet prefab that the enemy is going to shoot to the player. Okay, the next thing that we are going to do is just to implement the method shoot at player. Okay, just copy paste this whole code into your project, into the empty shoot at player. And what you should do right now is just to fix the compilation errors. So here we have a private member variable that we have to declare. Okay, so it's a private and it's a float. Okay, and we will initialize it to 0. This variable called timer to shoot, it will count the time in order for us to know when exactly the enemy is going to shoot at the player, because we want to shoot at the player in a certain frequency. Okay, and the frequency that you are watching right now on the screen is that we want to shoot to the player every 2 seconds. Okay, so with this private variable member, we keep track of the time that has passed. Okay, and when the time that has passed is above 2, then we will proceed to shoot. Okay, we will reset the timer for the next bullet, and we will proceed to create an instance of the bullet enemy. We will ignore that the bullet collider ignores the same enemy collider. We don't want that this bullet collides with the same enemy that produces it. Okay, we are going to set the type of the bullet. Okay, and the type of the bullet, we are going to move the types from the player to the bullet. Okay, and bullet enemy. Okay, let's fix it on the code. Okay, so bullet is the constant type bullet player is right now coming from the class bullet. Okay, and the type bullet enemy is the one that we are going to use in order to initialize the new bullet that we are going to shoot. Okay, so back on track, we create the instance of the new bullet. We use the physics utility to ignore the collision between the collider of the same bullet and the collider of the same enemy, the enemy that has generated this bullet. We get the type of the bullet. We get the position that the bullet is going to start. It's going to start just in the center of the enemy. And we are getting the direction from the enemy to the player. Okay, we get the vector direction that the bullet is going to follow. Okay, and with that information, what we are going to do is to get the component bullet, and in the component bullet use the method shot with the type, with the position, and with the direction to the player. Okay, going back to the Unity editor. Okay, we still have a compiler error. Okay, so we are checking it. So we are trying to use the constant that we have defined in bullet. Okay, so the name bullet is right, and the error we are getting is this one. The game object does not contain the definition of type bullet. This is not meant to be a game object, so we are doing something wrong right now. It's because, as you can see right now on the screen, we are getting the definition from bullet from the public variable member of the type player, and we are using exactly the same name of the prefab to the reference of the prefab bullet as the same name as bullet. So what we are going to do is just to rename this as bullet player. We can use the refactor, the rename functionality, to put it as bullet player. Okay, and now here we can make reference to the constant we have declared, and right now, yes, we are getting the reference to the class, we are getting the constant we have previously defined. Okay, but now back on the editor, we have lost the reference to the bullet. Okay, so right now there is no reference to the prefab because we have renamed it in the code, and we have to set it again. So no problem in something so small. Okay, so we set it again. Okay, and the next step that we are going to do is just to check the collision. Again, we are going to copy paste, and I am going to explain what we are doing here. Okay, so copy paste this code on the bullet class, and we are going to replace the whole on collision enter with this code. Okay, so what we are doing here is, okay, we are using the method on collision enter to detect when the bullet has collided with something. Okay, and we check the type of the bullet. Okay, do you remember that when we shot the bullet, we were setting the type? In the case player, we were using this constant, and in the case enemy, we were using this other constant. Okay, so we are checking that if the type bullet is of the type player, then it will check only against the enemies. Okay, the collision against the enemies, and if it collides with something else, it will just destroy. And if the type of the bullet is of the type enemy, it will check the collision against the player. If it collides against the player, then it will apply some damage. Let's go deeper in what we have done here. So what we are getting here is, okay, we are getting the collided object, and from the collided object we get the game object, and from the game object we are able to check if this game object has the component enemy. Okay, if it has the component enemy, okay, it's an enemy, and we can proceed just to decrease the life of the enemy. Okay, just as we did before. Okay, after decreasing the life of the enemy, we destroy the same bullet. since we are already destroying this right here, we can just do it like this, because after this if, it will always destroy the bullet. Okay, and in the case that the type is of type bullet enemy, if the collided object, the game object, we get the component and we find the component player in the collided object, it's okay, we have collided with a player. And what we are doing is, to that player, we are decreasing the life of that player, the damage value of the bullet. Okay, and finally destroying the whole thing. Okay, let's also move it from here to there, because if the bullet collides with something like the floor or like a wall, we will also make it disappear. Okay, so right now, if we did it right and we go to the Unity editor and press play, now if we get close to the enemy, the enemy will get close to us and he should start shooting to us. Okay, as you can see, we are receiving bullets and our life is being decreased. If we get away from the enemy goes back to the initial position. Okay, we are just one shot to be dead, so let's kill ourselves. So let's get close to the enemy. Okay, the enemy gets close and shoots and we are dead. Okay, I cannot move anymore. The finite state machine attached to the player, well, we have transitioned to the state died, and in the state died, as you can remember, we were not able to do anything else. Okay, so this is working, the behavior of the enemy is working. Let's repeat it again, just to summarize this part. Okay, so we are getting the behavior of the enemy was, if it's in range, it will move until towards the player, and if the enemy gets into shooting range, it will start shooting in a frequency of 1 bullet every 2 seconds, and if we get away enough of the detection range, the enemy will go back to the initial position. Okay, now in the detection range and now in the shooting range. Okay, so this is for the behavior of the enemy. We have completed the finite state machine for our enemy. Game programming and software programming in general are about being able to adapt the project to changing requirements, and that's what we are going to do in the next step. We are going to change the requirements of what we need for our enemy, just to adapt it to the new situation. Okay, so the changes that we are going to do are this one, that every time the enemy goes back to check for player, that's it, to go back to the initial position and keep checking if the player is inside its detection range. Okay, the moment it changes the state for check for player, instead of going to the initial position, it should go to a random position. Okay, so the goal would be, when the enemy loses track of the player, instead of going back to the initial position, he will go back to a random initial position. So what you are going to do right now is that you are going to download these 3 files. Okay, the file with the design diagram, the file with the state diagram, and also this pseudocode. Once you have everything ready, that's it. First, the enemy state design diagram, second, the table design, and finally the pseudocode. Now the first step that you are going to do is just to change the state design diagram, just to include the new behavior we need. Okay, so what we need is that when the player goes back to the check for player state, in that particular moment we need to update the initial position to a random position. So make the necessary changes in first in the state diagram in order to make this particular behavior. And the solution should look similar to this one. So what we are going to do is that in the moment that the player goes back to the state check for player, instead of going to the state check for player, he is going to go to a new state. In this new state, we will update the initial position to a random position, and once we have updated that position, then when the position is updated, then we can go back to the check for player state, where the player would go to that new initial position. Okay, next what you should do is go back to the diagram editor, and in the table you are going to add this new state to this table. Just create a new row and a new column, and just consider the new state. Okay, so go ahead and do it. And the solution should look similar to this one. Okay, so what we got here is that in the same state, what we are going to do is just to update the initial position to a random position. We will create a method that will do that, and we will just change directly the state to check for player, so he goes back to the initial state where the enemy was going back to the initial position that in this case has been updated. And the other change that we have made is that when the player was on the state go to player, and there was the transition to check for player when the player was not inside the detection range, this transition right here disappears, because instead of going directly to the state check for player, now we are going to the state that update random initial position. So what we have done here is this transition right here is has been moved to here. So when we are on the state go to player and the player is not inside the detection range of the enemy, then we transition to the state update random initial position. Okay, so these are the two changes that we have made. Okay, and now it's time to translate this new state diagram to pseudocode. Okay, so with that new state diagram, then we can create the new pseudocode. So go to the pseudocode and please do it. And the pseudocode should look similar to this. Okay, so we have created a new case, the case update a random initial position, and inside this case we are going to perform this action. Okay, this action that is this one, just to update the initial position to a random value and change the state to the check for player state. Okay, and we have also moved that instead of going when the enemy was on the state to go to player, and if it detected that the player was not inside the detection range, then it transitions to the update random initial position. So what we got in the pseudocode is that when the player is not inside the detection range, then transitions to the state update random position. Okay, so we have our pseudocode, and what we have to do is just the final step. It's implement the code. But before implementing the code, just remember not to implement this method yet. This method, just leave it empty, because what we are going to do first is just the case, the part of the skeleton, and in the next step we will do the update initial position. Okay, so just implement just the new case. Okay, so go to the code. Okay, and the solution should look like this. So we have implemented, wait, I have missed something. When we are on the state go to player, and the player is not inside the detection range, instead of going back to check for player, he's going first to update initial position. Okay, so we are done here. We have created the new structure, the new case, okay, to implement the behavior we are looking for. So the new case is here. As soon as it updates the initial random position, it will change to check for player state. And if the enemy is in the go to player state and the player is not inside the detection range, then he transitions first to update random initial position. Okay, so the next step is just to complete the behavior we are looking for, and what we are going to do is implement the method update random initial position. Okay, as a tip, you can try to Google by using this example, Unity random range example vector 3, and implement a way to update the initial position to a random position. Please consider that the y component of the initial position should remain the same. The only two values that you need to change are the x and z, so please consider that when you are creating the new random position. Okay, so now go ahead and do it. And the solution should look similar to this. So what we are doing here is to our initial position we are assigning a random value, but we are only setting as random values the values x and z of the vector component. And we are using the utility that has Unity engine, that it's random, and range. And range, what it does, it's just right here, return a random integer within a range of values. Okay, so if everything works as expected, if we go back to the Unity editor and press play, we should be able to reproduce the behavior we are looking for. Okay, so we are going to get close to that particular enemy. Okay, and we are going to trigger its finite state machine. by just entering inside its detection range. Okay, so he's in detection range, and we are getting out of the detection range in order for the enemy to go to a random position. So we are out, and as you can see, the enemy is going to a new random position. Okay, let's try it again. Let's enter inside its detection range. Okay, we are inside the detection range. He is shooting right now. Okay, we are good, and we are going to leave its detection range. Let's see where it goes. Okay, so it's going somewhere else. And it has reached the new initial position. Okay, we have successfully implemented the behavior we were looking for. And now we are going to do the final step of this lesson, that it's an improvement on what we have just did. If you have noticed, the state update random initial position is only executed once. Okay, because after just updating the initial position, it just changes to the check for player state. Okay, so in reality, for this particular case, we don't need a new state. We have done this just for you to understand that you have tools in order to adapt your project, your code to new requirements. But in this particular case, for an action that is going to be run just once, we have other ways to do it more efficient. Okay, so in order to perform some actions just only once, when we are just changing, in the moment that we are changing the state, to these one-time actions performed in the change of the state, we can extend the behavior of our design table just by with these lines, these diagonal lines, allows us to define that the actions that are going to be performed once in the moment that the condition is met. Okay, so what we will have is that when a condition is met and we require to perform one-time actions on this change of state, we can just draw a diagonal right here and place the one-time actions to be performed in the exact moment that a state is changing. Okay, so what you are going to do now is just that, is download the diagram. Okay, and in this diagram what you are going to do is just that, implement the behavior of changing the initial position to a random position when the enemy goes back to the check for player state. Okay, so go ahead and do it. And the result should look similar to this one. In the exact moment that we are going back either for the state go to player or for the state shoot to player, they go back to the state check for player. In that exact moment, when we change the state, we just update the initial position. So now what we are going to do is just to translate this table diagram design into our pseudocode. Okay, so go ahead and do it. Okay, and the result should look similar to this. We don't need anymore the new state. Okay, and what we are doing is that in the moment that we are changing the state check for player, we are also performing the operation of updating the initial position to a random value. Okay, and we are doing it for both cases, that in both states go to player and shoot to player. As soon as the player is not inside the detection range, it will update its initial position and update go to the new state check for player. Okay, now go ahead and implement this solution into the code. And the solution should look like this. We have deleted the state we created before, because we don't need it anymore. And on both go to player state and shoot to player state, as soon as it's detected that the player is not inside the detection range and changes the state to check state player, we update the position to a random position. Okay, question. Is there a better place where to put the action update or random initial position? Okay, so just think about it, because right now in the code we are calling it twice. Okay, we are calling it well, in both cases that the player is outside the range, and going back to the check for player state, we are calling it twice. Okay, think about if there is a better place to call the one-time operation update initial position. Please give it a thought and come back with ideas. Okay, you may have remembered that we extended the method change state in order for us to, well, just to perform an operation just in the exact moment we change the state. We did it for that moment. We only were just displaying a debug log message just in the exact moment we were transitioning between states, just to know what was going on. Okay, but we can use that to be able to perform one-time operations. In this particular case, we know that when we are going back to the check for player state, we are going to update the initial position to a random value. Okay, so what we have done here is that instead of duplicating the code and having to update random positions right here, just in the moment that the change state was called, in this exact moment we perform the one-time operation of updating the initial position to a random state. This extension of would prove extremely helpful to perform one-time operations, things related to initializations. You will see that it has really many utilities that we can take advantage of. So please keep it always in mind that you have a place that when you change of a state, you can perform one-time operations. Okay? So the only thing left to do is just to go to the Unity editor and play the final result. And we should get exactly the same behavior as we ran it before. So if we get close to the enemy will go towards the player, okay, and if we get away from the enemy is going to a new initial position, okay, and he will stay there until the player is inside its detection range. So this whole thing is still working as expected. Okay, just for the sake of testing, let's move away from the enemy, and the enemy will choose another initial position. Okay, so what's next? What I recommend you to do is all these steps that we have done for the enemy, from the creation of the finite state machine through the diagram until the full implementation of that finite state machine. I recommend you to do exactly the same for the case of the NPC. Okay, first of all, you would start creating a finite state machine like the one of the enemy, okay, but in this case for the NPC. I am considering the NPC that is not going to kill the player, but maybe to talk to the player. Okay, so that's a behavior that can change from shooting to talking. Okay, after doing that finite state diagram, you should convert it to a table design. Okay, you should get a table design for the case of the NPC. After that, you should get the pseudocode for the NPC. Okay, and finally you should implement the code. Okay, so this is optional homework. The result is implemented in the next code checkpoint, but I strongly recommend you to do it.